Hello and welcome back to Calculus 1, section 3.10 on derivatives of inverse trig functions. So we have 6 trigonometric functions, sine, cosine, and so on, and then there are 6 inverse trigonometric functions, labeled as either sine to the minus 1 or arc sine, depending on which corner of the world you're coming. The difference between the two is that sine of an angle, let's say pi over 6 radians, is 1/2. Inverse sine of 1/2 will give you the angle back. So that is what the inverse means and the way we use it. Inverse in general is going to undo the function. So now we would like to know, because we understand that these inverses are functions as well, we would like to know what the derivatives are. Now there is a way to derive these through standard procedures of you swap x with y and you just run your implicit differentiation. Everything is worked out in a book if you're interested in derivation and the proof. I'm going to run the formulas and I'm going to show in detail which way these are used. And you will use 2 more than the other 4. I'll spell it out. So we start with the derivative of inverse sine. And that is 1 over square root of 1 minus x squared. The next one is the derivative of inverse tangent. One over 1 plus x squared. And the derivative of inverse secant as 1 over absolute x times the square root of x squared minus 1. Now, the other 3 will have the same formulas, just with a minus sign. So I'm just going to change sine into cosine, tangent into cotangent, secant into cosecant, and put negatives everywhere. So to save time here, I'm just going to copy this and then make those few changes. And I guess you get to write everything from scratch. So sine is going to be a cosine. We get minus signs everywhere. Tangent is going to become cotangent. And secant is going to become cosecant. There we go. So these are your 6 inverse trig functions. The question is, do you get to use them in this form? And clearly the answer is no, because most of the time you have the chain rule. Oh, I forgot to mention, so the 2 that you will use the most are inverse sine and inverse tangent. So those are the ones that will show up in your Calc 2 differential equations and so on. So those are the most frequent ones. The other ones are rare. We use them to, to flex in mathematics and do some mathematical gymnastics. So are you going to see sine inverse of x? In most cases, no. You're going to see sine inverse of x squared plus 3, sine inverse of e to the x squared, sine inverse of ln of 3x. So most of the time you're actually going to have a chain rule which modifies these formulas, and that is the key to learn which way to modify the formula, because most of the time we are going to stare at the derivative of sine inverse of some function. So most of the time we are staring at that, not just basic vanilla x. Now, what do we know? So if on the left side you replace x with f of x, then common sense on the right side, every x gets replaced with f of x, and then the 1 in the numerator gets replaced with the chain rule, which is f prime. So the formula for this, which is the one that you would use most of the time, is f prime of x divided by the square root of 1 minus f of x squared. The one for tangent, right? So these are the two that show up most of the time, is f of x, f prime of x divided by 1 plus f squared.
Where's that exponent there? F of x squared, is that above the x? The denominators of those?
Over here?
Yeah, where is that 2?
Well, it was squaring x before, now it's squaring f of x. The entire function, like f of x squared, right. But we generally just write it this way.
Oh, okay.
So now we have, these are the ones, so pretty much all of your problems in the future are going to fall in this, unless, as I said, you are flexing in mathematics. So what is the derivative of sine inverse of e to the 4x? Well, you know that your f of x is e to the 4x, so just plug it in. 1 minus e to the 8x. The derivative of this is 4e to the 4x, and you're done. These problems should take, on average, about 27 seconds, which includes thinking and writing. Where is mine? Oh. So, sine inverse, f of x, e to the 4x. So f of x is e to the 4x. You can bring it right on the side. So you write that your f of x is e to the 4x. And then you see that to compile the answer, you just need to plug here the f of x original and its derivative there. So what's f prime? Is 4e to the 4x. You know that from before. So here we go. You replace your f prime with what f prime is, 4e to the 4x. 1 minus, instead of f of x squared, you put e to the 4x squared, but 4x times 2 is 8x. So e to the 8x. And just walk away. As I said, about 27 seconds per, right? And you either know the formula or you don't. There's no, you can't make this stuff up. The derivative of inverse tangent of x cubed plus 3x squared minus 7x plus 1. Just to make it as annoying as possible. Again, the derivative of the argument, that's 3x squared plus 6x minus 7. And then in denominator, 1 minus, we have x cubed plus 3x squared minus 7x plus 1, everything squared. Done. What happened?
The derivative of arctangent.
Oh, It's 1 plus, yes. Holy nightmare. I did the inverse sign, you're right. It's 1 plus.
So you don't have to expand the bottom?
No.
Oh.
Because eventually when this stuff pops up in your chapter 4, you say equal to 0, and then cross multiplying it, it kills denominator completely. So you never have to worry about denominator, which is always good. Technically only focus for the numerator. Let's do inverse cosecant because we can. Inverse cosecant of how I toss in some ln because it's fun. Ln of square root of x. How about that? Now I'm going to. I never converted that formula for you into the f of x state. So let's see what you get. So I'm just going to give you the original formula and then see if you can convert it into f of x formula and then actually do the problem. Tonight. Okay, let's take a look at this. So we first upgrade the formula from x to f of x. So the formula would be negative f of x prime divided by absolute value of f of x times the square root of f of x squared minus 1. That's the first part. Now we know that our f of x is equal to 1/2 ln x. Yeah. The x has the exponent of 1/2. You can kick it out and eliminate the chain rule. Long live logs. Right? Repeat. Long live logs, right? So now we also have that the f prime of x in this case would be 1/2x. Right? Because it's 1/2 times 1/x. So now all I need to do is to plug these into the formula and I'm done. So instead of f prime, I have negative 1/2x. In denominator, I have absolute value of 1/2 ln x. And then I have the square root of this squared is going to be ln squared x over 4 minus 1. Clean it up. If I multiply numerator and denominator by 2x, in the numerator I just get negative 1. In denominator I don't need absolute value anymore. I will get x ln x square root of I needed a 4 over here, so we should multiply by 4x because I need 2 on the outside to kill a half, but I need also another 2 that when goes under the square root it will become a 4 to kill the over 4. So now the numerator is now 2, negative 2, and then I take 2 to kill this one and 2 to kill this one, so that's ln squared x minus 4. There we go. Yep, walk away.
Why isn't it 2 on in the denominator?
I'm sorry?
In the denominator, why isn't it 2x times ln x?
I have 1/2 a times the square root of b over 4. Okay? So if I multiply this by 4, because we're only talking coefficients, right?
Okay.
I'm going to break this 4 into 2 times 2. The first 2, red one, cancels the half. The second 2 will cancel the 4. That's the blue one. Because when this 2 undergoes the square root, it will become a 4. Because it gets squared. When you stuff something in a square root, it picks up a square. When you take it out, it loses a square. So this 2...
Bless you.
Oh, thank you. Oh. So this 2 gets stuffed underneath and becomes a 4. Right? If you have a 4x, that's 2 root x. Well, if you stuff this 2 back inside, it will become 4. So anytime you stuff something under, it picks up a square. If you stuff it under the cube root, it picks up a cube. So that's why I'm multiplying by 4, because I need 1, 2 to kill this, and another 2 which will become a 4 to kill that. Which is also the reason why this is 4. Because when it undergoes the root, that 2 becomes a 4, it cancels on the first but multiplies into 1 on a second to become a 4.
So I get under the root now, but I don't understand why 4x times 1/2.
Just 2 times 1/2.
Well, this one needs to be understood as 2x times 2. So 2x will multiply the first one, and you get your 2 canceling a half, and here's your x extra, this one. And then the other 2 is the one that goes alone under the root, becomes a 4, and fixes that. And on top you have negative 4x divided by 2x, so that's just negative 2 on top.
It's a modified version of 1.
Well, yeah, 4x over 4x, sure. You saw me first start with 2x and 2x because all I looked at was a 2x and a 2, completely disregarding this 4. Then I had to bump it up. Good.
Could you do that in like in 2 steps, like, because I feel like my brain would not process that. So like, could you do it as 2 times the numerator and denominator to get rid of the fractions at first, and then to get rid of the fraction inside the root, you can do it again?
Yes. So you can do it into yes.
Okay.
So originally I had 2x and 2x, but then I noticed this one. That's why I bumped it to 4.
Okay. So it's just you skipped a step.
Mm-hmm.
Okay.
Oh. But then if you factor it out, you would have to factor a quarter from here. It becomes a 4. Might be more confusing, but it will work, obviously.
Well, I would multiply under the root by 4, and then I would multiply everything else by 2 again.
Mm-hmm.
Okay.
Anything else? Yes.
On the exam, you said you're going to pick 2 out of the 6, right? Okay.
Not this one.
Anything else? All right, then that's a wrap.